In this video, we're going to go over our first example of a graph algorithm called K-coloring or graph coloring. So I'm going to just have you go ahead and do graph coloring because in its nature, it's really not that complicated. It's something that most people could do just with a small graph on their own without any algorithm. So the question is, assign a color to each vertex such that no two vertices connected by an edge have the same color. What is the minimum number of colors needed? So we're going to start off by noticing that there are three vertices or nodes that are connected here in the middle. And so we know that none of them can have the same color. So we'll start by coloring each of them a different color. Okay, so I'm going to do that one red, and I'm going to do 5 purple, and then I'm going to do 3 blue. Okay, so then I'm going to go from those nodes out. So 5 isn't connected to anything else, so we're good there. But we can see that the 2 is connected to 0, and it's also connected to 4. So those can be any color except for red. So I'm going to go ahead and make those two a different color. So I'm going to just choose to make them both blue. So that can be blue and that can be blue because 0 and 4 are not connected to 3, which is the blue one. And then as far as the last node, it's only connected to 3, so it can be either red or purple. So I'm going to go ahead and make it red. And so total, I only needed to use 3 colors in order to color this graph based off of the criteria that no two vertices connected by an edge have the same color. So we can look through and check every edge, and we can see that along every edge, the 2 vertices that are connected by that edge are not the same color. So the minimum number of colors needed for this particular graph is 3. Now this isn't the only way to color it. There's lots and lots of different ways to color this graph via that criteria. And this problem is called graph coloring. Now the question we asked wasn't what is the colors of the graph, but the question was what are the minimum number of colors, which is 3. So regardless of all the different ways that you could color it, you would find that there are no fewer colors that you could use than 3. This type of problem comes up in all sorts of different applications, particularly really interesting graph applications. And what's really interesting about this problem, graph coloring or K-coloring, is that so graph coloring in general or K-coloring is that there is no efficient way to write this algorithm. So it's something that you'll cover, I think, in your algorithms class in 401 if you go on to take that class. But it is part of computer science theory that you'll learn about, and if you're really interested you can start reading about it now. But you've maybe heard about NP-hard problems, NP-complete problems, but this is one of the NP-hard problems. It is a problem that we don't know how to efficiently solve. We can solve it. You can use greedy algorithms to solve it, which is basically like this is not technically correct, but it's basically like a guess and check method where you just like do the best you can as you're walking through the graph. It's very similar to the algorithm we just used in order to color this graph, which is like we just went to a node and we colored that one, and then we went to its nodes and colored it based off of that one. That's basically what a greedy algorithm is. It's like a local decision. So you just like kind of go for it. And unfortunately, it's not deterministic. So, as you apply the greedy algorithm, you could get different coloring, depending on how you applied the greedy algorithm. But this type of problem is really interesting because it's still something being studied and still something being determined, just like the whole idea of NP-hard in general in CS theory. But that doesn't mean it's not used all the time. It is. And we see graph coloring all over the place. So I'm going to tell you about, it's probably I think graph coloring is probably my favorite algorithm. It's like my favorite idea, because there's been so many times when I've thought of something, particularly like when I've thought of an assignment that I wanted to write for this class, and then I've realized it's a graph coloring problem, which is an awesome problem to solve, but unfortunately it is not easy to autograde. So kind of leaves you stuck. So what I'm going to do is I'm going to show you one example which connects to CS261. So even if you haven't taken 261 yet, that's okay. You'll still understand this this application anyway, but it'll also get you ready for 261 if you're taking it next semester. So one of the things that you'll learn in 261 is that you're going to kind of learn how code goes from C++ down to machine level code. And what happens at kind of machine level is that compilers translate this language that is already arguably barely human readable down to basically decide on the actual device itself, like where are you going to place the data in order to do the calculations. And these are called registers. So basically there's only a few of them in the computer, and so someone has to write the code that decides in what order you actually process the code that's written. So in a function, if you have this function here, you have a couple of calculations, a couple of branches, how do you actually decide where to store all of this local memory that you need in order to execute this function on just a few registers? That's kind of the question. And doing it well makes for faster running of your code, and that's how compilers are optimized. So, the fastest way to do a calculation is to put it in a register rather than accessing its memory. And so you want to be able to optimize the use of the registers. So in this particular function, the function called f, there are 6 different variables. A, B, and C are passed in as parameters, and x, y, z are local to the function. So if we wanted to optimize this particular function to run down at machine level in these registers, how many registers would we need to store 6 variables if we wanted to use the minimum number of registers possible? So the answer is that we need 3 registers, but let's talk about how we can determine that. So this is called a liveness analysis, and it's determining like through the life cycle of the function how long is a particular variable needed. So we're going to define a variable as live if its value is still needed in the future. So what we're going to do is we are going to write up a list of all 6 variables that are used in this function. And then what we're going to do is we're going to go through and determine how long they are live. So A, for example, if you read through this code, A is passed in as a parameter, but if you look down along the whole life cycle of this function, you'll see that A is never used. So A is never live, and we never need to store it. So what's cool about compilers is even if you write bad code, compilers will read through your code and actually be like, you don't use that, so I'm not going to save it, you know? And so A is never a live variable. B, on the other hand, is used in this line here. And then after it, B is never used again. So B is live from the start when it's passed in as a parameter all the way down to that line, and then it's not needed anymore. C, on the other hand, is used in a couple different places, but you can see that it's used all the way down here on this line. So we're going to need access to C until it's used in the definition of X. Now X is used a couple different times. X is used here where it's defined, and then it's used again here. So it's defined and then it's used right below it. But then you'll notice that X isn't used again in the remaining code. It's again defined right here and then used immediately underneath it. But in between those two places, the value that's stored in X is never used. So it's only used in these two short segments it's only live for these two short segments within the life cycle of the code. Y is defined here when it uses X, and then Y is used here. So Y is live right here. And then Z is the last one. So Z is used in the if statement, and so depending on which location is true, it'll either be on the line of the if branch or the line of the else. And then Z is used in the X definition. So Z is only live between the if-else branch and the definition of X below. So this is the idea of what's called liveness analysis. And we could see from this analysis that basically at any one time, we can see that the max number of variables that need to be known is just 3. And so this is kind of getting your head wrapped around this whole idea of how you could possibly determine how many registers are needed for a particular function. And so the liveness analysis can tell us that, but we can actually also tell this from using graph coloring. So you might wonder how that's possible. So what we do is we write out each node or each variable as a node. And then I'm going to pull up my liveness analysis, and I'm basically going to connect two nodes if they're ever live at the same time. So an edge represents two variables that are live at the same time. So if I look at my liveness analysis, I can see that I'm just going to go from left to right. B and C are live at the same time, so those are going to be connected. C is also live at the same time as X. I can also see that C is live at the same time as Y. And then I can also see that C is live at the same time as Z. So C is live at the same time as B, X, Y, and Z. And then if we go to X, X is live at the same time as C, but it's not live at the same time as anything else. Y is live at the same time as C, but Y is also live at the same time as Z. And Z is live at the same time as Y and C. So the resulting graph we get is here. This represents the each vertex or node represents a variable, and each line between those nodes represents that those two variables are live at the same time. So in this slide, I kind of showed you that the minimum number is just by looking at, the maximum number of variables live at the same time. But this would be hard to do for a large program, and it's also not natural for a program to do, right? But with graph coloring, using a graph coloring algorithm, which again is possible to solve it, it's just not possible to solve it deterministically in an efficient way. We can get that same result by just doing graph coloring. So the way that we'll do that is we can again see that we have 3 nodes that are connected. So I'm going to color this one red, and then I'm going to color this one purple, when I go down here, it makes it very hard for me. I'm going to color this one yellow, and then I'm going to color this one green. So those all 3 have to be different. So if I started at any one of them and got to the others, I would know that I would have to color them all differently. And then from here, A could be anything, right? A is not connected to anything, so I can just make it whatever color I want. Green and since B and X are both connected to C, neither of them could be green, but they could both be either other color, right? Because they neither of them are connected to Z. So I used 3 different colors to do the graph coloring, and so that is how we know it is a minimum number of registers would be 3. And I'm going to change the yellow one to purple because it's easier to tell the difference. So this is just one application of graph coloring with the registers. So what you'll notice is that the graph coloring is often applied to problems where you're trying to find relationships between things and minimize the number of conflicts, I guess is the way you could think of it. So all these other applications of graph coloring have that same nature. So the most famous one, and the one that kind of started off a lot of the work in graph coloring, is coloring maps. So a planar map, like the map of the United States, the map of any country or state. If you want to color different states or different cities or different regions a different color so that no 2 touching regions are the same color, there's a couple theorems that prove how many total colors you would need to ever do the coloring of that map. And so that's one example of a problem that uses this idea of graph coloring. There's actually really interesting applications with scheduling. Scheduling is actually tricky. So final exam scheduling is a great example. So each student takes different classes, and those classes have different schedules and also exam schedules. And so in order to create a final exam schedule that doesn't have any conflicts, it's actually a graph coloring problem. And that's why it's so hard to do without conflict, because it is a really big graph when you look at a university system trying to schedule the exams. And so it's really hard to solve it without conflicts depending on how the actual classes are scheduled. So you can solve it well if you plan the actual schedule of the classes around what would make sense. But if you don't, it's really hard. So you basically create nodes that are each class, and then nodes are connected if if a student could be in both classes. So the nodes are the classes and the connections are classes share common students, and then it's just graph coloring. And so you can figure out our schedule by coloring the whole graph of classes uniquely so that no two nodes are the same color, and then each color is a different time for the final exam. So that kind of scheduling issue, room scheduling, scheduling in times, anything like that is graph coloring. Other interesting applications, storing chemicals. So let's say that you don't want to store chemicals that are gonna explode together. So you could have a graph that keeps track of that relationship. Store is a very similar application would be like enclosures at zoos or pet stores. If you can't keep certain plants or certain animals together in the same enclosures, that relationship would be similar. So Sudoku puzzles, seating maps, trying to create maps where people who have certain relationships are seated next to each other. There are tons of networking applications of graph coloring, and all sorts of different applications of allocating resources. At the end of the semester, we actually see we're going to meet a couple people from industry and people doing research here at UIC, and we'll learn about some of their applications of graph coloring as well. So stay tuned for that. That'll be exciting. I didn't include any of those here so that you could hear about those from them. So that's it for graph coloring. It's a really hard problem, but it's a really interesting one.